Okay, we started talking about modular equations, where you have an equation using the three lines, and you always have a modulus. Now, these are actually practically useful, and they're used in the supermarket in UPC and ISBN codes. Let's take a look and see how that works. So I'm sure you've seen codes like this on products you've bought in the supermarket, canned goods or vegetables and so on. Okay. There are 12 digits in this code you can verify, and this code is correlated with these lines. Now, in order to make sure that the code is scanned correctly, there's a relationship between these digits, and the relationship is expressed in this modular equation. All right, notice how the pattern here. Through the 12 digits are D1 through D12, so here's D1 and here's D12. And the UPC code is designed such that 3 times D1, in this case that would be 3 times 0, plus 1 times D2, which would be 1 times 5, plus 3 times D3, which is 3 times 0, plus 1 times D4, etc., etc. You alternate 3, 1, 3, 1, and so on. You get up to 3 times D11. D11 is here, plus 1 times D12. And the digits must satisfy this modular equation. It must be equivalent to 0 mod 10. Okay, that's how the numbers are chosen. You think about it, you could choose the first 11 numbers, and then you would be forced as to the identity of the 12th number. Okay. All right, so in this exercise you verify that this modular equation works for this code, and here you verify it's not code. So here's some other examples that you can do. This problem talks about transposition error. For instance, sometimes the scanner may get the numbers wrong. Instead of scanning like this, blah 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 30043-6, it might scan 30034-6. Now you want to avoid a misscan, so it turns out that if the scanner does read 30034-6, that's not a valid UPC, and the scanner will try again. It will know that there's something wrong with the scan. Okay. So most transposition errors, when the two digits are interchanged, are detected, but there are some cases where they're not detected. Okay. Sometimes also one single digit is not scanned correctly, and here we look at an example where a single digit error is detected. Now, what I didn't tell you is how these lines are related to the digits here in the code. But that really has nothing to do with modular arithmetic. That's just some other code that's used to relate the line configuration to the numbers. Now, the point is that the lines do represent a sequence of 12 digits, and you want to make sure to get all 12 digits correct. Okay. Here's a neater way of writing the same relationship between the digits. Here we have the digits. Here I go up to dk for generality, and each d is multiplying we could call this a weight w, and add it together. So this should be familiar in terms of the inner product that you see in vector mathematics. This is the inner product of these digits, these barcode digits, times the weights, and these weights are standard for each code. You see, we've talked about UPC. There's another code called the ISBN code. You've seen this on books. In this case, the weights are different. The weights are the numbers from 1 to 10. And in this case, the modulus is 11, not 10. Okay, so here you have several exercises where you need to check this out. The mod 11 means that we're going to actually need 10 different possibilities, and the character x is used as the 10th possibility. So in this ISBN, this x counts as 10. Okay. All right, so here's some other exercises with ISBN codes. So we get to solving modular equation. Now, in the case where we wanted to verify a valid UPC code, we had a modular equation like this. Notice we actually have 12 unknowns. Okay, so you certainly can't solve this uniquely for all 12 digits unknown, but if you know some of them, you can find the others. Okay. So for instance, if you wanted to find the last digit here, knowing these 11 digits, you could come up with an equation with a single variable. Okay, so the question is, how do you solve in general modular equations that look like this? Now, in the case of a UPC, we know that this x has to be a number between 0 and 9 because all of the code digits are between 0 and 9. However, in some cases we might want to find the most general x that satisfies this modular equation. So we need a technique or method in order to be able to solve equations in general like this. So here's one particular example where you have a modular equation. So we know how to deal with equations with equality. So let's see if we can turn this into an equation with an equality. Okay. Remember what modular equivalence means. It means that the one number minus the other number is some constant times the modulus. So 8 plus x equals 6 means 8 plus x is equal to 6 plus some multiple of 11. So that's expressed by this equation. Right? So we can solve this like any other equation. We get x in terms of k. Now k can be any integer. Okay. So what does this mean? This means that x is minus 2 plus any multiple of 11. And that's just the same thing as saying this equation here. X is congruent to minus 2 mod 11. Okay. Now there are many numbers that are congruent to minus 2 mod 11. Minus 13, 20, 130. All of these are congruent mod 11. And so these are just as valid ways of writing the solution. However, there's only one way to write this modular equivalence using a number in the integers mod 11. Okay? None of these numbers, minus 2, minus 3, 20, 130, none of these numbers are actually integers mod 11 because integers mod 11 are between 0 and 10. Now the number, we'd have to find a number between 0 and 10 that's different from minus 2 by a multiple of 11. And that turns out to be 9 because minus 2 plus 11 is equal to 9. 9 is equivalent to minus 2 mod 11 and it is a number in Z11. So this is the preferred way of writing the solution to this equation here, this modular equation here. We prefer to find x that's a number in Z11, and any number that's equivalent to that number, mod 11, is a solution. Okay, so that's what it talks about here. That the textbooks always write solutions in terms of numbers in Zn. Okay. All right. So far we have a general method. That's kind of what we want to do, is take our examples and generalize so that we can solve any equation that we encounter. Okay. So what were the steps we took in solving this equation? First, we turned the modular equivalent sign into an equal sign. And then you have to introduce an additional variable k. You had k times the modulus. Okay. Now, you find the value of k that puts x in the appropriate range, and then change the equation back into equivalence. Okay, so you can try that here. Remember 3 steps. Take this, change this into a equal sign. You're going to have a k times 3 in your equation, and then you're going to find the value of x that's between 0 and 2. And then you'll change it back to a modular equivalence. Okay, so these are modular equations involving addition. Let's think about the case where we actually have a linear equation and we multiply the variable times a constant. So this is a little more complicated, but we can still do it. Okay, let's start out the same way. We take this modular equation, and we know that what this means is that the left-hand side is equal to the right-hand side plus some multiple of the modulus. So this equation here is equivalent to this modular equation here. But this equation has an ordinary equal sign. Okay, since this is an ordinary equal sign, we can use basic algebra on it. We've changed from modular arithmetic to ordinary arithmetic. So we use the rules that we know and love from high school. Okay, so we solve for x. All right, now the point is that x must be an integer. Okay. To make x an integer, we must guarantee that the right-hand side is an integer. Okay, you can find that by trial and error. You find some k in Z5, some k between 0 and 4 that makes this an integer. Okay. And so it turns out that you get k equals 4. Now, if you add 5 times n to this value of k, you're still going to get an integer. Why is that? Because you've got a 5 in the denominator, and that 5 in the denominator will divide out the 5 here, and we'll still have an integer left. Okay? So we can actually make k equal 4 plus 5n, and that will all still make x be an integer. Okay? We plug that back in. We plugged in k equals 4 plus 5n, plug it back into the equation, get this result that x equals 10 plus 11n. So x is congruent to 10 mod 11 is a general solution. Okay? And it's a good idea to check your solution, make sure that it actually works in the original equation. Okay? The original equation, remember, was this one here. 5x plus 3 is equivalent to 9. Okay? So you can follow such a procedure to find a general solution for x for such equations. Okay, this example pretty much goes through the very same procedure. You have this algebraic equation where x has a coefficient. We change this into an equality. We do the division. We want to make sure that this number is an integer. By trial and error, you find that k equals 2 makes this an integer. I can add 4n to k, and still it will be an integer. So I've replaced k with 2 plus 4n, and you end up with this equation, x equals 6 plus 11n. That's the same thing as saying x is equivalent to 6. X is equivalent to 6 mod 11. Okay, so that's another way of writing the solution. Okay, so here this generalizes that procedure. Okay, now this is a procedure that works. One problem is that one of the steps is trial and error. Now, when the modulus is small, you don't really have to try many things. For instance, in this problem here, mod 12, when you do the trial and error, you'd have to try the numbers between 0 and 11. Okay, but there are techniques to speed things up. We can look at this example. Now, the idea in these techniques to speed things up is always to reduce your numbers as far down as possible. So the important point is here. That when you're doing arithmetic mod n, you can replace any number with its remainder mod n, and the equation still remains valid. Okay, so in this equation here, since my modulus is 15, I can replace any number in this equation with its remainder mod 15, and the answer doesn't change. Okay, so let's take this number 79, for instance. If I take this number 79, well, let's see, 75 is 15 times 5, I believe. So that means that 79 is equal to 4 mod 15. So to simplify this equation, I can simply replace the 79 with a 4. Okay. Now 9 is equal to 9 mod 15. Can't simplify that. X is unknown. Can't simplify that. So at this point, all we can do is simplify to 4x is equivalent to 9 mod 15. Okay, so we've used our modular reduction to simplify our equation. Okay, so let's go on and do the next step. that we did before is change this modular equivalence into an equality. We'd get 4x equals 9 plus 15k. If you divide both sides by 4, you get this result. All right, now the point is we want to make the right-hand side be an integer. Well, we can simplify the numerator here and take out the integer part. How do you do that? Well, notice that 15k is 12k plus 3k, and this 12k divides by 4 evenly. Okay? So that's always going to be an integer. Similarly, 9 I can make as 8 plus 1, and 8 divides 4 evenly. So what I have here on the right-hand side is a part that's an integer, it's always an integer, plus some fractional part that's not automatically an integer, but this gives a condition on k to guarantee that we have an integer here. Or there's only certain k's that work for this expression. So when we find those k's, we'll find the value of x that we need. Now, if you notice, if you put k equals 1 here, then this becomes an integer. If I add any multiple of 4 to k, it's still an integer. So k equals 1 plus 4n is the general value of k that makes this to be an integer. We can plug that into my expression, plug it back into my expression for x, and I get this expression here. Really, there's a little part missing here. This should be, instead of 6, it should be 6 plus 15n, right? Because you do have the 15n also coming out of this expression, okay, when you do the multiplication. So that should be 6 plus 15n. Okay. All right, so you can follow through this similar example, does the same steps, and in this case it turns out that there's no solution. Okay, so read through this and see why there's no solution. There's simply no way to make this into an integer. Okay, here's some more exercises. All right, now several exercises here. Sometimes you still have large amounts of trial and error. There's something called the Euclidean algorithm that's a general method that can always find the solution without trial and error, and we'll talk about this later. So we'll stop here.